Welcome to the Picture Language Seminar. It's a happy day in Cambridge, but our last talk of the seminar this spring, and we'll continue in the fall. We're very pleased to have Shu-Heng Shao here from Stony Brook. He's going to tell us about what's done cannot be undone, the story of non-invertible symmetry. So the floor is yours, and we're looking forward very much to your talk.
Thank you. Thank you so much. Well, it's a real pleasure to be back home to give this talk. Let me first share my screen. All right. Hey, so please feel free to ask me questions, interrupt me anytime, for people in the room and also for people on Zoom. Right, so this talk, I will talk about a new kind of global symmetries that have drawn a lot of attentions in quantum field theory and condensed matter physics recently. The conventional global symmetries are described by group theory. Wigner's theorem, for example, stated that in quantum mechanics, every symmetry has to be implemented by a unitary or an anti-unitary operator. Now, one special property of a unitary or anti-unitary operator is that it has an inverse. Right? The dagger of a unitary operator is the inverse of that operator. And more generally, these operators form a group. And one of the defined properties of a group is that every element has an inverse. However, in recent years, there has been a lot of developments in a new kind of symmetry known as a non-invertible symmetry. As the name suggests, these are symmetries implemented by conserved operators that do not have inverses. They sound totally exotic, but actually there are a lot of applications in quantum field theory, in particle physics, in condensed matter theory, in quantum gravity, in string theory, and mathematical physics. There has been a lot of development, and they lead to new conservation laws, new selection rules, constraints on normalization group flow, confinement and deconfinement in gauge theory, and more. Now, at this point, you might think, to find such an exotic global symmetry without an inverse, probably you have to work very hard. Probably you have to go to 11 dimensions, maybe with 32 supersymmetry to find the simplest such example. But actually, that's not quite the case. In fact, in arguably the simplest quantum field theory of all, which is the 1+1 dimensional critical Ising conformal field theory, there's already a non-invertible symmetry. Now, let me just say a quick word about Ising conformal field theory, because perhaps not everyone is familiar with it, but it's in the lowest space-time dimensions possible, 1+1D. And Ising conformal field theory, being the first minimal model, has the lowest central charge, has the least degrees of freedom, is really arguably the simplest quantum field theory of all. And yet, there's already a non-invertible symmetry there. So the equations behind this non-invertible symmetry is given here. It's okay if it's the first time you see it. Let me just quickly go through it. For the rest of the talk, we will not need these three equations. So Ising model, by definition, has a Z2 symmetry. It flips the spin up degrees of freedom to spin down. That I denote by eta. It's Z2, so eta squares the identity operator. What's more interesting is that at the critical point, at the CFT point, in addition to this conserved operator eta, there's one more conserved operator D. It commutes with the Hamiltonian, commutes with the stress energy tensor. However, it does not have an inverse. It's an operator that has a kernel. And it does not obey group multiplication law. In fact, if you square it, you get a sum of the identity operator and the Z2. In addition to this simplest example, there are many, many more examples in 1+1D conformal field theory. But one question that has been there for many years is that, are those non-invertible symmetries special to 1+1 dimensions? Do we have this kind of new symmetries in general space-time dimensions, including our dimensions, 3+1? And that was what happened around the year 2021, where in a paper of mine with my collaborators and also another paper at the same day, we found very general construction of non-invertible symmetries in general space-time dimensions. And the quantum systems that realize this non-invertible symmetry, there are not some highly supersymmetric, bizarre, exotic quantum field theory. they include the conventional 3+1D U1 gauge theory, the free Maxwell theory, QED for the real world, which is the main subject of the talk today. QCD below the electroweak scale, axion physics, lattice gauge theory, string theory, and more. That has led to many developments. And last summer, we organized a TASI summer school, where we have a rerun of Sidney Coleman's famous lectures, aspect of symmetry. So if you're interested in this topic, you can see my TASI lectures from last year. For the remaining time of the talk today, I will focus on one particular example, instead of giving you a broad overview of all the examples. I want to focus on one of my favorite examples in this subject, which is the non-invertible symmetry in QED. And by QED, I really mean the 3+1 dimensional U1 gauge theory coupled to a single Dirac fermion. That's it. In fact, let me show you the Lagrangian. I mean, this is probably, I don't know, maybe the 5th Lagrangian everyone learns when learning Peskin and Schroeder. So this is a 3+1D QED with a massless unit-charged Dirac fermion coupled to the gauge field. F mu nu is the field strength for the gauge field. I denote the gauge field as A, capital A. Psi is the 4-component Dirac fermions, and they are coupled in the standard way. There's no minus sign because I work in the Euclidean signature, but that's not going to matter. Don't worry about it. All right. I also normalize my gauge field slightly differently if you are paying attention to the equation. I put the E squared in front of the kinetic term, but that's just for convenience. In this normalization, the integral of the magnetic field is 2 pi times the integer with no factor of the electrical. But modulo those little cosmetic things, this is really just the ordinary QED. Now, in QED, if you stare at this Lagrangian, there's a chiral symmetry that leaves the Lagrangian invariant. It acts on the Dirac fermion fields by a phase, but multiplied by the gamma 5 matrix. So what that means is that this rotation, it rotates the left component of the Dirac fermion and the right component of the Dirac fermion in the opposite way. That's why it's called a chiral symmetry. So I denote this by U1 sub A, where A stands for X. Alpha here is the rotation angle. There's a factor of 2. Don't worry about it again. I put a factor of 2 so that alpha is identified with alpha plus 2 pi. So alpha equals to 2 pi amounts to doing no rotation. This is because when alpha is 2 pi, you send psi to minus psi, but that's part of the gauge symmetry. So we should identify. Okay, so the classical Lagrangian of QED has this symmetry. And for years, people thought, okay, I mean, if the Lagrangian is invariant under some transformation, it has to be a symmetry. What else can you ask? Well, famously, as demonstrated by Adler, Bell, and Jacquet in 1969, this symmetry has an anomaly. And what do I mean by anomaly? I should really say that the word anomaly is the single most abused term in theoretical physics. Everyone has their own definition of anomaly. So whenever I talk about anomaly, I really make sure I give the definition of the anomaly I'm using here. I'm not saying that other people's definition are wrong, just want to be clear about what do I mean by anomaly in this talk. So by anomaly, I mean this is a classical symmetry that leads to Lagrangian invariance. But the ABJ anomaly says that this classical symmetry fails to be a symmetry quantum mechanically. Quantum mechanically, QED does not have U1 axial symmetry as a symmetry. That's what I mean by ABJ anomaly. It's the phenomenon where a classical symmetry fails to be a symmetry quantum mechanical. All right. Now, ABJ anomaly was discovered in the context of the neutral pion decay. ABJ used the anomaly to match the coefficients in front of the pi 0 FF tilde term or F wedge F term you are from FTH background. And the ABJ anomaly determines the coefficient here, which matches with the observed dominant neutral pion decay rate into 2 photons. Okay, so that was a beautiful story from the 60s that we all learned in textbooks. But if you think about it a little bit more, just conceptually, there's something slightly, and I really emphasize the word slightly, counterintuitive here. Now, what's counterintuitive about? Usually we celebrate when we find a global symmetry of the system. You find a new symmetry, great. Then all the correlation functions should obey the Ward identity of the symmetry. You use the symmetry to do an anomaly matching condition, and then you find new stuff. But in the context of the ABJ anomaly, it's the opposite. ABJ says that naively you thought there were a chiral symmetry, but actually there isn't. It fails to be a symmetry quantum mechanical. And just to demonstrate that I'm not the only person who interprets the famous work of ABJ this way, this is a picture I found on the internet. This is a logo for a conference for Steve Adler's 60th birthday at IAS in 1999. I wasn't there, but you can find it on the internet. Now, the title of the conference is Symmetry Found and Lost. And note the order of found and lost. The upshot of ABJ is that the symmetry at the end of the day was lost. Now, given that the symmetry was lost at the end of the day, how come we were able to derive all these beautiful quantitative results that match with experiments from the absence of a global symmetry? Wouldn't it be nice if we can reinterpret this classic result from the existence of a new kind of global symmetry, and rather than the absence there? So that's one motivation for the rest of it. Another motivation is the following question. If you see someone on the street, and you just ask him or her, is chiral symmetry a symmetry in massless QED? Now, what kind of answer are you going to get? Now, when I grew up, I thought the answer is just no, period. I mean, that's the upshot of ABJ anomaly. We don't have a symmetry at the end of the day, and that was also manifest from Steve Adler's 60th birthday conference. But then when I grew up a little bit, I realized that that's not the end of the story. Because if you look at QED, if you are just doing positron electron scattering all day long, tree level, 1 loop, 2 loop, you'll see that the amplitude, the scattering amplitude, is non-zero only when the helicity of the electron and the positron is conserved. So there's some kind of conservation law if you just play with the electron and positron. But what's the symmetry behind? Well, naively, the symmetry is the chiral symmetry. But that's not how we taught it in textbooks. So this is chapter 5 of Hastings and Short, where they explain the helicity conservation in electron and positron scattering. Now, if you look at the derivation, the way they derive it is that they move the gamma 5 matrix from one end of the trace to the other end. And then they find a minus sign unless the helicity is conserved. Now, they didn't dare to say that. They didn't dare to use the chiral symmetry to derive the helicity conservation because they knew somewhere down the road in chapter 19, the symmetry will become anomalous. Okay, so the situation is a little bit more complicated. Naively, there isn't a symmetry, but something is conserved. So what can we say? Well, another answer that people usually give, which is the correct answer, is that yes, it is a symmetry, but in flat space-time, because there's no non-trivial abelian instanton configuration that will violate the symmetry. But this is also not the full story. Because in flat space-time, you can consider the scattering of an electron of a very heavy monopole. And let me just be clear, by monopole here, I have in mind an infinitely heavy monopole. Just sitting there, it's not part of the spectrum of your quantum field theory. It should be viewed as a defect. The more technical term is the two-loop line defect of the quantum field theory. But for all practical purposes, think about it as an infinitely heavy monopole just sitting there. And you're just sending an electron which scatters off this monopole. This is a famous calculation done by Callan and Rubach, known as the Callan-Rubach. And what's interesting about it is that if you decompose the electron scattering into different partial waves, the lowest momentum wave, the S wave, actually violates the helicity conservation. So even in flat space-time, in the presence of monopole, you see that this conservation law does not always hold. So after this, so maybe the right thing to say is that fine, it is a symmetry in flat space-time, and if there's no monopole. Okay, after this lengthy discussion, I hope I already got you confused. And in fact, I think the standard answer to this simple-minded question is both yes and no. And I hope everyone will agree with me. If you ask someone a yes or no question, the worst answer you can possibly expect is yes and no. So another motivation for the talk today is that can we give a different answer, or maybe a reinterpret? I'm not saying anything was wrong in the literature, but is there a different way to look at a problem where we can get a straight answer? Okay, any question at this point?
So is the conservation given by self-adjoint charge?
Wait and see. But let me give you the answer. The answer is no. There is not going to be a gauge invariant charge at the end of the day. But let me proceed, and if it's still not clear, I'll get back to your question. But the answer is no. Oh yeah.
So it's actually in flat base. Why did you say that it's not a symmetry? There's
Because even when there's a monopole in flat space, the conservation law that would have naively followed from the symmetry is violated. So you can say that it is a symmetry in flat space time, and if there's no more. That's a true statement. I'm not going to debunk that statement. Later on, the very modest thing I'm going to do is just to give a reinterpretation of this thing.
Yeah, it's a very naive question, and you'll no doubt answer it. Why do you call this a symmetry? Are you using symmetry and conservation law interchangeably?
Good. So later on, I'm going to be very explicit about what I mean by symmetry.
Okay.
And by a symmetry, I mean a conserved operator. This slide is just to show that in the literature and in the community, people, we use the word symmetry in a careless way. And that could lead to different people use it in different ways. And that could lead to different kind of conclusions. For the rest of the talk, I will be very explicit about what I'm going to identify.
So that was
From
the
this-
same question I asked. Yeah.
Exactly. And that will be clear later on. But for this slide, I haven't defined what the symmetry is. And that's part of the reason what led to all this confusion. Some people think symmetry has to be, a continuous symmetry has to be associated with a conserved Noether current. Some people think that has to be associated with a conserved charge. If you ask Wigner would say, oh, well, you just have to come up with a unitary operator to me, and I will call it a symmetry. Different people have different definition of symmetries. Okay, I'll be explicit about what I mean by symmetry.
Yeah, the presence of monopoles will change the geometry of.
Very good. So indeed, the presence of the monopole essentially changes the topology. So if I want to be really economic, I can just say this sentence is still correct. I'm totally fine with that. It's just that sometimes when I say that, other people don't like that presentation. So I elaborated it. But I absolutely agree. Any other question? Great. Okay, so the upshot of the talk is that I will argue that the invertible chiral symmetry of the classical Lagrangian for 3D is not entirely broken by the decay. Rather, it is resurrected as a non-invertible global symmetry, labeled by the rational. So originally, the symmetry is labeled by that alpha, which is a angle variable, but we are only going to resurrect the rational part out of it. And in the pion Lagrangian, one can rederive the coupling constant in front of pi 0 f wedge f by matching the non-invertible global symmetry. All right. So now coming back to Howard's question, what is the symmetry? So let's start easy. Let me start with the ordinary U1 global symmetry associated with the honest to God Noether current. And let's just make sure we're on the same page for the ordinary. So I have an ordinary conserved Noether current, J mu. D mu J mu vanishes. That's the conservation equation, local conservation equation. Given this equation, what do? I take the time component of the current. I integrate it over the whole space. That is the charge. That's the charge that Arthur was asking me. Given the charge, I can further exponentiate it. and put a little angular variable alpha here. And that gives me a unitary operator, which I denote by U sub alpha. It is conserved, meaning that dt U alpha vanishes. And that will be my working definition of a symmetry for the rest of the talk. This is a necessary condition for symmetry. This is not a sufficient condition for symmetry. And I will let me not say too much about what I think will be the other conditions that append to the symmetry. But at the very least, whenever I have a symmetry, I will hope that there is a conserved operator that commutes with the Hamiltonian or the stress tensor in quantum field. In this case, this U alpha is the guy. It's invariant under time evolution, and more generally, you can if your space has a more general topology. So let me code my three-dimensional space as M. This is the three manifold at a given time slot. Then by writing the conservation equation in the differential form notation, I can write a unitary operator on this general three manifold as the integral of star J. And in plain English, that just means that I take the fourth vector and integrate it along with the normal vector of the three. Now, in the story of QED, we didn't have the luxury of an ordinary conserved local conservation. The current there is JA mu, A stands for axial. It's a fermion bilinear with an important factor of gamma phi. Now, here in gray, I write the anomalous conservation equation in component form, but here I use the differential form notation. So gradually in this talk, I will switch to the differential form notation. So a D star JA does not vanish. Rather, on the right-hand side, you get F wedge F. That's the instanton number density for the V linkage field. So the name of the game is that given this equation, which was derived by ABJ, can we find a conserved operator? And by conserved, I just mean I want to find an operator that commutes with the Hamiltonian. Well, let's see what we can do. The first thing you will try is just to take star JA, it's a differential three form, integrate over your spatial manifold M. Well, but that is not going to be conserved because the right-hand side does not vanish. So when you apply the Stokes theorem, you cannot freely deform this manifold M. So our first trial just failed. Well, let's try again. And that's exactly what Adler did in his 69 paper. He talked about this operator, where he shifted the integrand by a term ABA. In component form, you have this epsilon tensor contracted with A derivative and A. This term is known as the Chern-Simons term later on. Okay, so why did he define such an operator? The reason is because the thing, the parenthesis here, star JA minus 1 over 8 pi squared ABA, is a closed differential three form. In other words, written in components form, this is a conserved current. Okay, well, that seems to be good news. Given a closed form or conserved quantity, I can integrate it over my three manifold and presumably get a conserved operator. But there's a slight catch here. First, the thing in the parenthesis is not gauge invariant. Gauge field is not gauge invariant. Gauge field is shifted under the gauge transformation. ADA is not gauge invariant. Okay, so we don't have a gauge invariant current. Well, you might cross your fingers and hope that maybe after the integral, we do get a gauge invariant charge. And that was Arthur's earlier question. Do we get a gauge invariant charge? But the answer is still no. And here I'm just going to quote a fact. And you are not supposed to question me about this fact. This fact is that the Chern-Simons action, this quantity, is the integral of ADA, exponentiated, is gauge invariant if and only if this capital N is an integer. There's a slight factor of 2 issue regarding the spin structure, but again, don't worry about it, just chill. So this quantity, this integral is not gauge invariant. Even if you exponentiate it, it's only gauge invariant for some very specific choice of the coefficient out front. And you can see that this coefficient can only be achieved if alpha is a 2 pi times an integer. But that amounts to doing the trivial chiral rotation. So no value for alpha between 0 and 2 pi will this quantity U hat be gauge invariant. And that's the reason I put this operator U hat in quotation marks. And that's the convention I'm going to adopt in the rest of the talk. Everything that's going to be in quotation marks are not gauge invariant, and they're waiting to be fixed.
So in the previous slide, is this, in the slide before this, with the this operator would be, this is the operator that implements the chiral symmetry of classes 2D that will be preserved in flat space at access point.
Actually, no. This is not conserved even in flat space. So in flat space with no monopole, this operator becomes gauge invariant. And it gives you the helicity conservation and everything.
So the statement that you're making about the chiral symmetry of classes 2D, that's just a statement about preservation of helicity.
That's one consequence of the chiral symmetry, of the classical chiral symmetry. And in flat space-time with no monopole, trivial topology, it follows from this operator. But the moment you want to talk about monopole, this guy is not good enough. And that's what I'm getting at next. Any other questions? Okay. So we tried twice. Now, before proceeding to the third try, let's be less ambitious. Pick our angle alpha to be 2 pi over n, where n is just some random integer. It could be 7, 17, 100, up to you. And let me put this value of alpha into this gauge non-invariant operator U hat. Okay, so I didn't do much. I just put this value of alpha in. And you see this problematic piece, which I'm marking red, is 1 over 4 pi n. It's still not gauge invariant. It's only gauge invariant if the integer is in the numerator rather than in the denominator. So we didn't achieve that. Well, but the reason I want to bring this up is because this term, red, made a famous appearance in a completely different physics context. That's the fractional quantum Hall. So the fractional quantum Hall effect, is a tabletop experiment. The physics happen in two-dimensional space, and then there's a time direction. And in fractional quantum Hall effects, this red action is commonly used as an effective response action to describe the physics. But even though it's the same equation, the physical interpretation is completely different. Remember, M in the previous slide used to be your entire three-dimensional space at a given time slice. Here, M is going to be your 2 + 1D manifold, where your condensed matter experimentalist friends work in. In the previous slide, A is a dynamical gauge field, which will create the photon one-particle state. On this slide, this A is a background gauge field for the magnetic field your experimentalist friends set up in their lab. So it's a completely different interpretation, but it's the same action. And this action describes the nu equals to 1 over n fractional quantum Hall effect. But you might be wondering, wait, our experimentalist friends, they do real physics and some of them won the Nobel Prize out of this. Now, how come they use a gauge non-invariant action to describe something that's measurable? Well, the story is that in that context, there's a well-known fix to this gauge non-invariant action, which I put in quotation marks. The more precise and gauge invariant Lagrangian for the fractional quantum Hall effect is this blue action, where I have introduced an auxiliary gauge field little a. Now, in this blue action, both terms are properly quantized. You have the integer in the numerator rather than in the denominator. What's the relation between the blue and the red? If you naively integrate out the little a gauge field, you should think about it as some auxiliary gauge field. Then you get this relation. The little a is capital A divided by capital N. However, both little a and capital A, they are properly quantized U1 gauge field with normalized magnetic flux. And you cannot divide the properly quantized gauge field by a factor of n. That will ruin the magnetic flux quantization. And that's to be expected. The red action is not gauge invariant. The blue action is gauge invariant. It's impossible to relate a gauge non-invariant action to a gauge invariant action by a legal manipulation. So this substitution must have its fallacy. At any rate, in the context of the fractional fundamental Hall effects, you should take the blue action as the more precise gauge invariant action for the physics. All right, so this is one slide describing the fractional fundamental Hall physics. And motivated by this, what I did with my student, Licho Choi, who is graduating this summer and moving to IIS, and with my longtime collaborator, Hotao Lam, who's a postdoc at MIT. In 2022, we were motivated by this discussion in fractional fundamental Hall physics, and we replaced this problematic piece of the U-hat operator by the blue action in the fractional fundamental Hall physics. Yeah.
Can you say a few words on why the naively equation for motion are turning out to be not gauge invariant? I mean, usually I would have an action, I would get the equation for motion. And I should have a gauge invariant thing.
So you can certainly try to integrate a little a, but first of all, the relation you get is a relation between the field strength, right? Not in terms of the gauge fields. So I removed the derivative in writing down this equation, and that's the imprecise part. So at the level of the field strength, if you don't care about electric and magnetic fields, you can divide it by n, no problem. But the issue is that for the gauge fields as a globally wrong. Okay, so back to QED. We replace this problematic piece by the blue action that is perfectly gauge invariant. And define a new operator in QED. So on this slide, again, M is your three-dimensional spatial manifold. And D is an operator. What is an operator? An operator is something that acts on the entire space at a given time. So it depends on the space, and you insert it at a given time, your path integral or whatnot. Now, the interesting feature about this operator D is that I need to introduce an auxiliary gauge field little a that only lives on the spatial three manifold M. And I have to do this path integral whenever I want to compute any observable involving this operator. But you should just think about it as an auxiliary gauge field. So let's think about, what are the features of this operator D? First of all, for any integer n, I can have this d1 over n. So I get infinitely many of them. In fact, it's easy to generalize the rotation angle to any fractional value, number times 2 pi. You just have to replace this blue action by a more general 2 + 1 dimensional TQFT. Anyway, there's a TQFT for every rational fractional state. This operator is gauge invariant because both coefficients are properly complex. It is also conserved. Now, why is it conserved? One heuristic argument is the following. When you check something is conserved or not, in Euclidean space-time, you are checking if you can locally deform the locus of this manifold M. And since it's only about the local physics, you can integrate out little a freely. That's the heuristic argument. The more rigorous argument was provided in the paper, where we use gauging to argue that it is really conserved. But at the end, oh, sorry, there's a question.
Is this small a has a dynamic on the
Excellent. So
that term?
excellent question. Excellent question. First of all, it's a field that only lives on the three manifold, so it definitely does not have any term in the bulk Lagrangian. In the bulk, you still have the good old-fashioned, the fifth Lagrangian you learned in quantum field theory class. And this is the operator you insert at a given time acting on your Hilbert space. All the states in your Hilbert space are just the photon state, positron state, electron state. I didn't change the Hilbert space. This A is only defined on this on the support of this operator. It only has this Chern-Simons quadratic term. It does not have the Maxwell term. In fact, if you had added the Maxwell term, that would ruin the conservation of this operator. It's really tied to the topological nature of these two blue terms. Yes.
But presumably this TQFT has like some dimensional number space. Do you like answer that with the original number space? Or?
Yeah, in a way you can think about it that way. So, but it's the essential thing is the following. Here, I'm giving a path integral presentation for this operator. So I'm not changing the Hilbert space that this operator is acting on. you can say that this degrees of freedom I'm introducing can lead to new degrees of freedom when you try to use this operator to twist your Hilbert space. But I'm not doing that. Okay. So what do we have? In the third trial, we have an operator that is both gauge invariant and conserved. And intuitively, you can say that the fractional bound whole state cures the Ising. And we can repeat the same again for every rational numbers. But for irrational numbers, I don't see a way to generalize the story just because there's no irrational state. However, okay, but there's no free lunch in theoretical physics. So something has to go wrong slightly. Is this operator unitary? Well, how do you check if the operator is unitary or not? You take the operator U, multiply it by U dagger. If it's 1, it's unitary. If it's not 1, it's not unitary. It's as simple as that. So let's take this operator D and multiply it by its dagger. How do you take the dagger? When you take the dagger, you flip the sign of the imaginary number I. But that's not the key part. If you flip the sign of the imaginary number of I, you can see that this piece in black will cancel between D and D dagger. However, we have to introduce an auxiliary gauge field A for both D and D dagger. So we will have 2 gauge fields. And when you multiply them together, they do not cancel with each other because A and A bar are 2 different auxiliary gauge fields you introduce for the 2 operators. So you get a rather complicated expression. And the only thing you need to know about this operator on the right-hand side is that it's not identity. And the only justification I'm going to give at this talk is that it doesn't look like it. But okay, but jokes aside, actually I wrote 2 entire papers about this operator. This operator is known as the condensation operator in condensed matter physics these days. And you can rigorously study how it acts on the Hilbert space, and you'll see that it actually has a kernel, so it cannot be the identity. But I'm not going to explain all that details in this talk. So we see that this operator D is not unitary. In fact, we can furthermore show that it has a 0 eigenvalue in the presence of magnetic flux. So it's not only non-unitary, it's also non-invertible. So let's look at the scoreboard for the 3 operators we just talked about. In the first trial, we talked about this operator U. It is gauge invariant for whatever it's worth, but it's not conserved. In the second trial, this is the operator introduced by Adler. It is formally conserved, but it's not gauge invariant. In the third trial, we talk about gauge invariant operator, which is also conserved. The only price you pay is that it's non-invertible. I want to argue that it's really a feature, not a bug of this operator. Yes.
So there's a type of operator that comes up a lot in mathematics called the partial isometry.
Yeah, you did mention that. Yes, yes, yes.
U dagger and U dagger U are projections.
Yes.
Not necessarily identity.
Yes, yes.
Is that what is going on here?
Yes, yes, yes. And it's manifest. You made the same comment when I gave the Ising talk.
Oh.
Yeah, and in the very last slide. Yeah, and we actually add that comment to the paper in D2.
Right.
Yeah, yeah. And I will have a table comparing the 2 cases.
Yeah.
But the answer is yes. Very good. Very good. Okay. So that is the operator. How does it act? Well, let's talk about it. So the way I'm going to work in Euclidean signature, the way it acts on the fermion fields is just by chiral rotation. It's completely invertible on the fermion fields. And that is why when you do positron electron scattering all day long, you're not going to see any hint of non-invertibility. The story only gets interesting when you try to introduce a heavy monopole warp. In the technical term, the 't-Hooft line defect. So this H is a 't-Hooft line defect in space-time. This is the war line for the very heavy monopole. And when you try to add this operator, which I show in red, on this 't-Hooft line, what happens to it is that the 't-Hooft line experiences a Witten effect. And what is the Witten effect? The Witten effect says that if you shift the theta angle, then the monopole turns into a die. And what happens to this 't-Hooft line is that when you add this non-invertible operator on it, it becomes a dionic line. But a dionic line with a fractional electric charge. So it's not really a line defect anymore. It's attached to this integral of the magnetic flux, which I'm showing. So the fact that this operator does not map a genuine line defect to another genuine line defect, this is hallmark that is a non-invertible. For people who have studied Ising model in details, the analogous picture is that the non-invertible Kramers-Wigner operator maps the order operator to the disorder operator. Order operator is a local operator. Disorder operator is not a local operator, it's a string operator. Here is a souped-up version of that in 3+1 dimension, where the non-invertible symmetry maps a line defect to a surface defect. And this, the very fact that the 't-Hooft line transforms under this non-invertible symmetry explains that in the Kalin-Rubakov effect, the felicity conservation, the felicity is no longer. Yes.
So, I might miss this. Can you explain how this is a diagram? This surface defect?
Right. So this surface, what is this surface defect? So 't-Hooft line is can be defined as a boundary condition for your gauge fields. Now, so that's what's happening on the left-hand side. On the right-hand side, in addition to that boundary condition, you also integrate F in this blue region. Now, F is just your magnetic field. So if you integrate F on some surface with a boundary, you are very tempted to write F as dA and apply the Stokes theorem and write it as the integral of A on the boundary of that line. But there's a problem in doing that because the coefficient here is not an integer. When you do that naive substitution, you seem to get a Wilson line with fractional coefficients along the orange line. And that would signal the Wilson line with fractional electric charge. It is in that sense, this object behaves like a diamond with fractional electric charge. But the more precise expression is the one I'm giving. Any other questions? Right. Well, whenever we have symmetry, we should ask the question about naturalness. Now, there are also many different notions of naturalness. Let me stick to one that is perhaps a little more old-fashioned. It's the notion of naturalness by 't-Hooft, like Hades. So 't-Hooft said, if you have a global symmetry, you impose the global symmetry, then the Lagrangian should include OG, so the global symmetry is G, the Lagrangian should include OG invariant terms with coefficients of order 1 with no fine-tuning. Great. Okay. So using in that notion of naturalness, you can say that the QED Lagrangian, what is the symmetry forbids you from adding the electron mass term? As I said, the non-invertible global symmetry acts on the fermion field as a chiral rotation. So now you can say that the electron mass is natural, the electron is naturally massless in QED because of the non-invertible. Now that sounds like an awfully fancy way to talk about naturalness in QED. And in fact, we should have asked, when 't-Hooft wrote the paper in 1980s, of course, 't-Hooft knew of the ABJ anomaly. So how did he think about it? That's this little blank space here, this one. So let's look at the little paragraph from 't-Hooft's 1980s paper. There's a little section called Naturalness in Quantum Electrodynamics. He said, QED, massless QED is natural, and the relevant symmetry here is the chiral symmetry. Blah, 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 here. But then he immediately said, we need not be concerned about the ABJ anomaly because the photon field being abelian cannot acquire non-trivial topological. And 't-Hooft was 100% correct. No, there's nothing wrong with this argument. What we are adding to the story is that you can alternatively view it as a consequence of a non-invertible symmetry. And when you phrase it in terms of the non-invertible global symmetry, you don't have to apologize for the absence of abelian symmetry. Okay, yes.
So is it true that all symmetries with an anomaly can be written as a non-invertible?
No, it depends on the details of the anomaly. In fact, in the story I'm getting at, in the context of QCD, we will also have an ABJ anomaly involving the strong interaction with SU3. Those symmetries cannot be resurrected as a non-invertible symmetry. And the simplest way to argue for that is that while we have fractional quantum Hall effects for U1 symmetry, we do not have a fractional quantum Hall effect for SU3. There's no way you can fractionalize the fundamental representation of SU3, but you can fractionalize the representation of U1. Sorry, so let me just finish. So it depends on the details. Sometimes it can lead to even more interesting higher symmetry structure. Here, I'm just focusing on particular.
You have the same problem if the manifold is not three-dimensional, like if there is some.
Generalization.
Five space
Oh,
vector.
yeah. So if you go to other dimensions, there are also similar generalizations. That's why people found a lot of generalization in string theory. In fact, in the beginning of the talk, I joke about 11D M theory and non-invertible symmetry, but that wasn't a joke. In fact, if you look at the 11D supergravity, there are similar non-invertible symmetries defined on higher dimensions, but that will be for another talk. Okay, so now let's quickly move to the pion physics. So that's also what we discussed in this 2022 paper. So I'm using the term QCD, but I really mean QCD below the electroweak scale. So the gauge symmetry is now U1 ENM times SU3. So below the electroweak scale, let's just focus on the first generation. And I'm taking the limit where the up and down parts are massless. In that limit, QCD Lagrangian has this chiral symmetry where we rotate the up and down part by gamma phi, but importantly, also with the sigma 3. If you remove the sigma 3, this will be the chiral symmetry associated with eta. And that symmetry has a mixed ABJ anomaly with SU3. I have nothing intelligent to say about that symmetry. That symmetry, as far as I know, is just broken badly. But here we are looking at the symmetry associated with the neutral pion. So this symmetry has a ABJ anomaly signaled by this triangle anomaly, triangle diagram. And by the exact same construction, we get all this non-invertible symmetry labeled by the rational numbers in QCD below the electroweak scale. Great. Now we all know QCD, when you flow to the low energy, should be described by the pion Lagrangian. So if we have an exact global symmetry in QCD, how does the IR pion Lagrangian match this global symmetry? So that's a very simple calculation you can do. The relevant terms you have to keep track of is the neutral pion. It's the compact scalar field pi 0. And here I assume there's a general coupling between pi 0 and FHF with a coupling constant G. For all I know at this stage, G can be 0. And then I take this operator, this non-invertible operator, and I insert it into my spacetime. And then I just ask myself, what are the equations of motion? Okay. So I have three different fields. I have the neutral pion field. I have the capital F, that's the bulk dynamical gauge field. I have the little a, which is here, that's the auxiliary gauge field. I have three fields, I have three equations of motion. If you stay at the three equations of motion for 5 seconds, you will see that they are only compatible with each other if this coupling constant G takes this value. That's the correct value.
What is that pi?
F pi is the pion degree constant, something like 93. It's the only dimension for quantity that sets the scale of the curve. Okay, so this gives a rederivation of the pi 0 FHF term in the pion Lagrangian, and we interpret it as matching an exact non-invertible global symmetry between QCD. That addresses the. Okay, so far we have re-derived a lot of known results. We have given reinterpretations of many things we already knew. Now, is there something new we can learn? What is it good for? So in the remaining time, let me go through some of the applications that we have. A very natural place to think about this non-invertible symmetry is the axion physics. So axion is a major target for new physics beyond the standard model, and in many phenomenological models, it contains a sector of a dynamical axion field, which I denote by theta of x, coupled to a U1 gauge field. So the action looks like this. Now I'm normalizing my axion fields such that theta is identified with theta plus 2 pi. Sometimes people like to put the axion decay constant into the normalization. Be a little bit better. Again, theta has the axion has a FHF coupling. So it behaves in a very similar way to the neutral pion. And because of that, all of the things we just discussed immediately apply. In fact, in many of the UV completion of this axion model, people use the Pechin-Quinn construction. In the Pechin-Quinn UV completion, you have a U1 global symmetry that has an ABJ element. And that is the symmetry that's going to descend to a non-invertible symmetry that shifts the axion field. So the upshot is that take this axion action, there is a non-invertible Pechin-Quinn symmetry that shifts the axion field by a rational number. And from that perspective, you can think of the axion field as a ghost number for the non-invertible Pechin-Quinn. The important thing about this of the axion physics is that this non-invertible Pechin-Quinn symmetry and many other symmetries are emergent. So what is an emergent symmetry? You have an energy scale here. And deep in the IR, you have axion couples to U1 with a lot of new global symmetries. But once you depart away from this strict IR limit, there will be a lot of stuff happening. Then putting them in this purple cloud. There could be dynamical axion strings. There could be dynamical molecules. There could be Pechin-Quinn fermions at a very high energy scales. And all this UV stuff will break the emergent symmetry there. However, even though the symmetry is emergent, they actually give you some organizing principle for how this UV physics can appear. So that's one application we found in these two papers. So the emergent non-invertible Pechin-Quinn symmetry mixed with other invertible symmetries. I'm not going to get to the details, but a consequence of this mixing lead to universal constraints on the possible UV completion elements. One thing we can say is that as you go up in energy scale, at some point you will run into the Pechin-Quinn fermion. At some other point you will run into the molecules. What the non-invertible symmetry can tell you is that the scale for the Pechin-Quinn fermion has to be much lower than the molecule scale. If you look at it, this might appear as the single most trivial inequality in theoretical physics. We're saying that the electron has to be lighter than the molecule. But of course, that sounds totally intuitive because the electron is so light, but we haven't seen the molecule yet. But on the other hand, it's also counterintuitive because we know in some gauge theory model, there are electromagnetic dualities. So the electron is supposed to be on the same footing as the molecule. In our case, it's the assumption we make that breaks the symmetry between the two. We assume that in the low energy, we have an axion couples to the gauge fields in this particular way. This coupling is not electromagnetic duality invariant. And this coupling tells you that as you will be completed, we have to have this hierarchy between the electrons. He also gives you constraints between the tension of the axion string versus the Pechin-Quinn fermion scale. So this is the kind of phase diagram that's dictated by the structure of the non-invertible. Yes.
So if you don't satisfy this equality, what breaks damage? You just not have non-invertible symmetry.
Yeah, that's one possibility. So what we can say is that if in the if in the IR you have this action, then you cannot violate these two. And you can take explicit Pechin-Quinn fermion model to check, and they always obey these two. There's a, yes.
There's a corresponding statement you can say about the mass of the Pechin-Quinn fermions, right? Because if I understand correctly, you're saying there is some constraint on the UV, right?
Yes.
This emergent symmetry.
Yes.
So those are two examples, but.
But this is N electric is the scale of the Pechin-Quinn.
Sorry, okay.
Yeah, I used the word electron somewhat irresponsibly.
Yeah, that's why
I actually meant electrically charged particle. In fact, when we submitted our paper to the journals, we got a complaint about that, and we removed all the words about electrons and replaced them by electrically charged particles. Thanks. There's also applications on the axion photon decay rate. So we had this paper from last September. It was coordinated with Matt Rees, where using the help of non-generalized global symmetries, one can derive a lower bound of the axion photon decay rate. Let me not get into the details of this. But one curious thing we found is that under many reasonable assumptions like post-inflationary axion domain wall problem, we find that the SU5 gut completions of the axion model somehow sit at the boundary of this inequality. For for reasons that we don't really understand. Okay, I want to spend maybe it's just the remaining 1 or 2 minutes on another application of a completely different flavor. So we talk about non-invertible symmetries in quantum field theory, in particle physics. But this symmetry is actually not exclusive to continuum field. They also exist somewhat universally in lattice systems with finite degrees of freedom. And the simplest example is to take a 1 + 1D quantum spin chain. So this is lattice system where you just have an array of qubits. So for any finite number of sites, it's a finite dimensional Hilbert space. And the simplest one already exists in the critical Ising lattice model. It's deformation. And the operator takes this following form. Actually, for those of you who were at my talk from a few months ago, this is the operator I talked about last time. So this xj and zj's, they are just Pauli matrices. So at the end of the day, this is just a gigantic matrix acting on your finite dimensional Hilbert space. You can show that this operator D does not have an inverse. It has a kernel. I'm just saying that the matrix has a 0 eigenvalue. There's nothing fancy. But it implements the Kerners-Wigner transformation in the following sense. And you can deform the critical Ising lattice model while preserving this non-invertible symmetry. And it actually gives you very strong constraints on the low energy phase time. So here I plotted a particular deformation studied by people in the literature. So at lambda equals to 0, this green dot is the critical Ising lattice model, where it is exactly solvable. This lambda deformation is a next to nearest neighbor interaction, preserving this non-invertible symmetry. And the phase diagram looks like this. There's an open region where the low energy phase in the thermodynamic limit stay as Ising compatibility. Then it hits a tricritical Ising CFT. Tricritical Ising CFT is the second minimal model. So I would say it's the second simplest quantum field theory. And after that point, the phase becomes gap, but with 3 superselection sectors. Now, you might by looking at this phase diagram, you might be wondering, how come we never run into a very trivial, boring gap phase? A gap phase with just one non-degenerate unique ground state. Why do we either have a gapless CFT in the green and the red part, or we have a gap phase with degenerate ground state? You might be wondering, is that an accident or a coincidence? Now, what we showed in this recent paper from January is that it's actually a general consequence of this non-invertible Kerners-Wigner operator. We show that every Hamiltonian that commutes with D in the thermodynamic limit must be either gapless or gap with the number of superselection sectors being a multiple of 3. Now, the number 3 might look curious. In theoretical physics, we see a lot of 2s, but 3 less common. But actually, there's a quick way to understand it. We should think about a model with non-invertible symmetry as having order and disorder coexist. In the disorder phase, you have one unique ground state. For high energy physicists, that's a Z2 unbroken phase. So think about it as a 5-4 potential. You just have the potential like this, you have a unique ground state. That's the disorder phase. But the order phase is the phase where the Z2 global symmetry is spontaneously broken. Think about it in terms of the 5-4 theory. You have a potential that looks like this. You have 2 ground states. This non-invertible symmetry says that disorder and order have to coexist. So if you have 1 ground state on the one side, 2 ground states on the other side, that add up to 3. That's the theory.
Yes, is that general? Like if I have Cn symmetry, like Cn generalization of this, would you have n plus 1 selection factor?
So the technical answer to your question is yes, but that's a misleading answer. Because you could have stopped your question as, is this more general, without saying the word Zn. So let me first answer that more general question. If you didn't specify Zn, the answer is no. You can consider Zn cross Z. Then the intuitive argument I just gave will fail. But if you somehow specialize to Zn, that coincidentally works. So there's a lot of details going into the proof that I'm not showing you here. So I'm cheating a little bit to justify the number of 3. And more generally, if you consider symmetry like Zn cross Zn, this reasoning will fail for a very interesting reason, The reason is symmetry protected topological phase. For Zn, you do not have symmetry protected topological phases. That's why this counting works. For Zn cross Zn, you do, and then this counting fails. All right, there are many more applications. I'm not going to go down the list, but I do want to mention one that I really like. Is this one. This one from, I think it was 2 months ago. So what these people show is that in two-dimensional integrable field theory, people like Zomological, they solve scattering amplitudes exactly in 1 + 1D integrable field theory. Those integrable field theory generally have non-invertible symmetry. So what they did is to take those scattering amplitudes.
Say who it is,
Oh,
because
I'm
they
sorry.
can't, online they can't see.
Okay, sorry, it's the item called crossing symmetry by Topodi, Lucia Cordova, and Shota Komatsu. In this paper, they found that they want to check whether the integrable S matrices discovered by Zomological and friends respect the non-invertible symmetries. Surprisingly, they found out that the integrable S matrices do not respect the non-invertible symmetry. So what went wrong? And they went back into the derivation. They found that actually crossing symmetry has to be modified in those integrable field theory. There's an overall factor that you have to modify because of the bizarre nature of the asymptotic state. And after you take that modified crossing symmetry into account, they found an integrable S matrix that's compatible with the So this is one example where the non-invertible symmetry pointed a mistake in the literature. Ironically, this paper was posted on a Sunday before a conference celebrating Zomological physics at Stony Brook. I asked Shota Komatsu whether that's on purpose. He said no, he's actually a nice guy. It was just so happened that the paper appeared on that day. So that's just one application, and there are many more. All right, let me conclude. So the title of my concluding slide is Symmetry Lost and Found. At the end of the day, we see that the QED actually has a non-invertible symmetry. And intuitively, it's a composition of the naive chiral rotation with a fractional all states. And if you allow me to put it in a maximally offensive manner, you can say that the neutral pion decays because of the symmetry. And there are several applications in axion physics, axion photon decay rate, and also in condensed matter. Personally, I think it's a very exciting time to be working on this subject on generalized symmetries. It's related to quantum field theory, to condensed matter, and quantum information theory, and also to string theory, particle phenomenology, and mathematics. There are several Simon's collaborations circling around this big idea. In addition, there are also a lot of activities going on. Okay, this is my last slide, so just 1 more minute, and I'll be done. So a few months ago, I gave a talk at authors group meeting about the non-invertible symmetry in the Ising lattice model. Today, I talk about the non-invertible chiral symmetry, 3 + 1 DQ. These are 2 completely different models. They're in different space-time dimensions. The model on the left even has finite dimensional Hilbert space. The model on the right is the physics that describe the photon, the electron, and the positron. It's infinite dimensional. And yet, if you look at the symmetry close enough, there's a lot of similarity. Both of them have a non-invertible symmetry. In the Ising case, it's associated with the Cramer's Wigner symmetry. In the QED case, it's related to the classical chiral symmetry. These are the expression of the non-invertible operators. In the Ising case, they are made out of Pauli matrices. In the QED case, they are made out of gauge fields. But if you look at them close enough, there are a lot of similarities. In the non-invertible chiral symmetry case, we have the invertible piece. This is the blue piece that implements the chiral rotation. In the Cramer's Wigner case, that corresponds to this piece in blue, which is a unitary. However, this unitary operator is not conserved, just like the naive chiral rotation is not conserved here. To fix that, in the QED case, we introduce an auxiliary gauge field A, and we do a path integral. In the Ising case, we add 2 terms together. So you should think about the path integral here as a pseudo version for the discrete sum in the Ising case. In the QE case, we introduce a 2 + 1 dimensional topological quantum field theory the topological quantum field theory for the fractional quantum Hall states to cure the anomaly. That's the red piece. In the Ising case, there's a factor of square root 2. Well, in the Ising case, what would be the analogous TQFT that you have to add to cure the anomaly? In QED, we have to find a TQFT that only lives on your spatial slice. So that's a 2 + 1D or 3D. Ising model is already 1 + 1. So the operating in Ising model is on just a one-dimensional line. So we are trying to find the topological quantum mechanics to cure the anomaly. What is the topological quantum mechanics? In quantum mechanics, any non-trivial Hamiltonian introduces a scale, and therefore it's not topological. So a topological quantum mechanics is just a finite number of ground states with no energy split. Namely, it's a qubit. But here, the fermionic nature is important. So we're talking about fermionic topological quantum mechanics. What is a fermionic topological quantum mechanics? That's a Majorana zero. And that's the solution too. In both cases, the non-invertible symmetries arise from an anomaly. In QED, it arises from the ABJ anomaly. In the Ising model, it arises from an anomaly involving the lattice translation of the Kitaev chain. In QED, the non-invertible symmetry exchanges monopole with diamond. In the Ising model, the non-invertible symmetry exchanges order with disorder. So even though these are two completely different models, they actually share similar symmetry. And I think that's really the beauty of symmetry. And with that, I thank you for your attention.
So thank you very much, Shu-Heng, for a beautiful introduction to your non-invertible symmetries. And I'm sure it's going to generate a great deal of discussion. Maybe there are questions here in the room. Yeah.
So those new kind of global symmetry, and are they feasible?
Excellent question. Sorry, excuse me. Excellent question. Some of them are, well, for ordinary symmetry, some of them are gaugeable, some of them are not gaugeable. In the modern terminology, those non-gaugeable symmetries are often referred to as having a two-hoop anomaly. So that's yet a different notion. For non-invertible symmetry, again, some of them are gaugeable, some of them are not. The Quermers-Wigner symmetry I talk about in the Ising model is not gaugeable. And that's related to the fact that it has such a dramatic consequence on the phase-time. And the way to gauge the non-invertible symmetry in Euclidean space-time basically insert, what do you do when you usually gauge gauge fields? You do pathing over the gauge field. So you're summing over all different possible gauge field configurations. For non-invertible symmetry, most of the discussion are about discrete non-invertible. And we just have to sum over all configurations of this non-invertible symmetry defect or on.
Are there other questions here?
Does non-invertible symmetry has any predictions about the thing that we could discover in this? Or it's just some restate some of the brains have found them.
Right. So in the axion discussion, I gave various universal inequalities that have to satisfy by any axion models. So and you remember there's one plot about the axion photon decay rate. So there, if someday we really see a axion photon decay process, we'll be able to put a dot somewhere on that plot. And the results here will tell you something about the global structure of the axion.
So are there any questions online? Any comments?
Yeah.
Is it always the case that these non-invertible symmetries are associated with some you just add some and some gauge dependence, or is it
The short answer is no. But for those that are easy to construct and explain, they are kind of this type. But there are more general ones that just have nothing to do with like classical ordinary symmetry.
Is there any non-invertible symmetry operator that you found of lower dimension, like or higher codimension?
Oh, yeah, absolutely. Actually, the history went in the opposite direction. So, you know, I started working on non-invertible symmetry in 1+1D from like 2017 or 18. And already at that time, it was clear that there are a lot of non-invertible symmetries in general space-time dimension supported on a higher codimensional. In fact, you can think about the non-abelian anions in topological order as such examples. What took us the longest time to figure out was how to construct non-invertible operator that acts on the entire space-time in general space-time dimension. And that was the development in 2020. So sorry, so it's one more comment. So whenever I say, you know, in the introductory slide, whenever I say, oh, it's hard to find non-invertible symmetry in general space-time dimension, someone in the audience will always raise their hand. Wait, actually, you know, people like John March Russell or Wilczek, Preskill, you know, they already thought about the Alice strings in non-abelian gauge theory in the 90s. Aren't those also examples? And indeed, they are. Those are early examples of non-invertible symmetry, but they are supported in higher codimension. So I think what has been new in the recent years are really all this codimension one. Yeah.
Sorry, I have a naive question. In terms of the Ising letters, we have a formula in this.
Yes.
It contains 3 parts.
Right.
And it has a square root of
Yes.
2 and a factor in the front.
Yeah.
Can we cancel that with has a denominator and denominator cancel the square root of 2 to get a meter formula?
So in the denominator, you have a 2. In the numerator, you have a square root of 2. You can combine the 2 together, but I find that conceptually less clear. But of course, it's the formula is what it is, so we can move the different pieces around. I present it in a particular way such that it mirrors the expression Q. Yes.
So I have a sort of a general question, you know, this is a rapidly developing field.
Yeah.
What is the most important challenging question right now that people who are working in this field are thinking about?
Yeah. I think the best answer is that there is actually no single most important question because it has so many applications. You know, some people are interested in applying this to hierarchy problem, to naturalness problem. These are important questions. But there's another community of people, you know, they work on condensed matter physics. They work on lattice spin system. And what they care about is how the non-invertible symmetry interacts with topological order, how they can be used to construct phase diagram. Then there's yet another community of people who are more mathematically oriented. They are interested in how these symmetries can be described mathematically. This is one of the few cases, actually, I think physics is a little bit ahead of mathematics. You know, I wrote down this operator D. What's the mathematics behind? It's some very complicated higher fusion category that's totally above my pay grade. But as physicists, you know, I just play with fields in Lagrangian and we can get something interesting out of it. So I think it really depends on who you ask. And it might sound like I'm giving an irresponsible answer, but on the other hand, I feel like that's my honest opinion, that there are so many different, I mean, symmetry is such a guiding principle in theoretical physics, and it doesn't really just have one application. There are just so many directions to explore.
So I think that's a good point to thank you
Well,
for
thank you.
giving us.